The electric field is an alteration of space around anything that has electric charge. The electric field is a vector field, which means it has a magnitude and a direction at every point in space. Finally, the units of electric field are newtons per coulomb. This is the equation for the electric field of a charged point particle. It depends upon the electric permittivity, the net electric charge of the point particle, and the distance from the point particle to the position where the electric field is measured. The vector r hat is a unit vector. According to standard definitions, this vector points away from the point particle. Since all variables except q in this equation are positive, the variable q, together with r hat, determines the direction of the electric field. For positively charged particles, particles for which the variable q is positive, the direction of the electric field is the same as the direction of r hat. For negatively charged particles, particles for which the variable q is negative, the direction of the electric field is opposite the direction of r hat. Thus, electric fields point away from positively charged particles and toward negatively charged particles. Let's calculate the electric field of this system of two charged point particles at the position P. It is easiest to calculate these electric fields by first determining the magnitude of the field. We can then determine the associated direction based upon the charge of the point particle. This is likely easier than determining the direction using r hat for each particle. The magnitude of the electric field of particle A depends upon the distance between particle A and the position P. We can determine this distance using trigonometry. After performing these calculations, we see that the magnitude of the electric field of particle A is the charge of particle A divided by 8 pi epsilon naught. We can determine the direction of the electric field using similar triangles. Specifically, the triangle for the x-axis and y-axis components of the electric field must be the same as the triangle used to determine the distance from particle A to the position P. Thus, the magnitude of each of these components is equal to the magnitude of the electric field divided by the square root of 2. Since particle A has a negative electric charge, its electric field points towards it. Thus, the electric field is in the negative x-axis direction and negative y-axis direction. We can perform a similar calculation for the electric field of particle B. However, since particle B has a positive electric charge, its electric field points away from it. Thus, the electric field for particle B is in the negative x-axis direction and the positive y-axis direction. The net electric field of this system is the summation of the electric fields of each of the 2 point particles. It is important to remember that in this expression, the variables q sub A and q sub B are the absolute value of the electric charges. Thus, q sub A equals 4 nanocoulombs and q sub B equals 3 nanocoulombs. We already took care of the effects of having a positive or negative electric charge when we determined the direction of the electric fields of particle A and particle B.